This is LeetCode number 1 2sum. For this problem, we are given an array of integers nums and an integer target, and we need to return the indices of the two numbers such that they add up to target. We may assume that each input would have exactly one solution, and we may not use the same element twice. We can return the answer in any order. Our constraints are nums.length is between 2 and 10 to the 4th, so that means we can have anywhere between 2 and 10,000 elements in our input. Nums I is between 10 to the negative 10 to the ninth and 10 to the ninth. So each element in our input can be big, small, positive, negative, 0, and same for target, and only one valid answer exists. So only one pair of numbers in our input sums up to target. In the example they give us, nums is an array with the integers 2, 7, 11, and 15, and the target is 9. So are there two numbers that add up to 9 inside nums? Yes, 2 and 7. So what we need to do is return the indices of 2 and 7, which are 0 and 1. So what if the target were 4? Are there two numbers inside nums that add up to 4? Well, you can say that 2 and 2 add up to 4, but remember that we cannot use the same element twice. So there is no output here. So how do we go about finding a solution to this problem? Well, we need to find two numbers that add up to target, right? So let's just call them A and B, and their sum is equal to target. And let's say that target is equal to 26. So what we can do is we can start at the beginning and say A equals 2, and look for B among the remaining elements. If we do some simple algebra, B is equal to target minus A, which is equal to 26 minus 2. A is equal to 2, B is equal to 24, and we need to look for B among the three elements 7, 11, and 15. So since B is not equal to 7, 11, or 15, then we need to move A over and start over. Next, we say A is equal to 7, and we need to look for B among the remaining elements 11 and 15. So B is equal to 26 minus 7, which is equal to 19. And 19 is not equal to 11 or 15, so we need to go to the next iteration. Next, we say A is equal to 11, and we need to look for B among the remaining elements, 15. And B is equal to 26 minus 11, which equals 15. So is B among 15? Yes. The solution to this problem are the indices of 11 and 15, which are 2 and 3. Next, we need to calculate the time and space complexity for this problem. For the time complexity, you see here, we iterate through n-1 elements, and then n-2, and then n-3 elements. And we do this n-1 times. What that simplifies to is O of n times n, which is O of n squared. And for the space complexity, it's just going to be O of 1 because we're just using two variables, A and B, to represent the two numbers that we need to find. So next, let's ask ourselves, can we do better than O of n squared? Well, one of the things we can do is seeing where we're doing repeated work and then making that more efficient. So if you see here, we are iterating through 11 and 15 twice. And you might say, well, twice isn't that much. Well, that's because our input is small. What if we were to add a few elements at the beginning of our input? And by a few, I mean let's add 1 million ones right here. So now our diagram would not look so small and compact, right? The first time we go through this, we'd say A is equal to 1, so B is equal to 25. And we need to look through 1 million plus numbers, and then 11 and 15. And we said, oh, we couldn't find a 25 here, so now we say A is equal to this one, and B is equal to 25. So we need to look for 25 among all these 1 million plus numbers, and then 11 and 15. And then we said, oh, we couldn't find a 25 among these numbers. So now we need to go through this process 1 million plus more times until we finally say A is 11, and so B is 15, and is 15 among the remaining elements? We said, yes, we found 11 and 15. But that was after iterating through 11 and 15 1 million plus times. So that's not very efficient, is it? The key here is, and let me erase all this. The key here is when we visit an element, we are going to store its value. And number two, we are going to need to be able to retrieve the value that we stored as fast as we can. And there are two data structures that we can use to do this, a set or a hash set or a hash map. And both of these we can store and retrieve elements in constant time or O of 1 time. So these two are ideal for this use case. So should we use a set or a map? A set will allow us to store the values, for example, 2, 7, 11, and 15 as we iterate through the input. But if you remember, our answer needs to return the indexes that the two numbers A and B, which sum up to target, are located at. So we need a map because a map will allow us to not only store the value, but also the index it's located at. For example, 2 is at 0, 7 is at 1, 11 is at 2, and 15 is at 3. So how would we use a hash map to solve the problem? Let's take a look. Our input is again going to be 2, 7, 11, and 15. And our target will again be 26. And again, we need to find two numbers, A and B, that sum up to target. And we're going to start off at the very beginning and say A is equal to 2, except this time we are going to have a map to store the index and the value as we visit each element. First, we say that A is equal to 2. So what does B equal? Well, B equals target minus A, which equals 26 minus 2, which equals 24. And we check, does 24 exist inside of our map instead of the remaining elements here? And no, 24 does not exist in our map, so we need to add 2, which is at index 0, to our map. And next we say A is equal to 7. So B would equal 26 minus 7, which is 19. Does 19 exist in our map? No, it does not. So we add 7 to our map. And we say, if A is equal to 11, does B, which is equal to 26 minus 11, which is 15, exist in our map? No. So we add 11 to our map. Next, we say A equals to 15, and we say, does 15 exist? Sorry, does 26 minus 15, which equals 11, does 11 exist in our map? And yes, it does. 11 exists at index 2, and 15 exists at index 3. So 15 plus 11 equals 26. And we need to return the indexes of 15 and 11, so 2 and 3. And so our answer stays the same, except we did this way faster. If you notice, we only visited each element once. So our time complexity is O of n, and our space complexity is O of n as well, because we had to use a map to store the values in their indexes as we visited them. Next, let's take a look at the code. First, we are going to initialize our output, which is an array of size 2. And at the very end, we're going to return our output. Next, we need to initialize a map that will contain our values and indexes as we make our way through the input. So that's what this map represents. Next, we need to look for two numbers inside of our input nums, a and b, whose sum equals target. So suppose our nums is 2, 7, 11, and 15. We need to iterate through these four elements to find a and b. So iterate through nums 2. So for int I equals 0, I is less than nums dot length I plus plus. Int a equals to nums I, and int b equals to target minus a. First, we need to check, does b exist in our map? So if b exists in our map, let's say, for example, we are at this point in time where a is equal to 15. So we've already visited all these elements and stored them inside of our map. A is 15, sorry, B is equal to 11, so we're checking, does B exist inside of our map here? So if map contains key B, then we know that we found our answer. And this else condition is B does not exist in map. So if we found our answer, that means output 0 equals I, and output 1 equals map dot get B. And if B does not exist in map, then we would simply add A to the map. So, for example, if our target were, say, 27, and A is equal to 15, then B is equal to 12. So we say B does not exist, therefore we're going to add 15 to our map. And we're going to put the value A, the index it's at, I, inside of the map. So here we can either break out of this for loop or return the output, and this will allow us to run our code a little bit faster. So let's run it and see how it does. Okay, great, it passed. Thank you for watching this video. Please like, comment, and subscribe.